Hello everyone, so today I'm going to try and diagnose an antenna problem, or at least hope to. Alright, this is an idea for someone else. Now, at the moment, because I'm in my unit, I don't have much room for antennas, so at the moment we're playing with a 2-meter antenna. So all I've done is I've got two pieces of wire, soldered them very dodgily onto an SMA connector, and as you can see, yep, you pretty much will get the normal, the little plot where you start at open circuit, you go through 50 ohms and then back to open circuit, or at least you're supposed to. There is a little bit of funny stuff happening up here, but that's okay. This is not the best antenna install. It's against my table, so there you go. Now, what I think is happening, I'm going to turn this into a balanced transmission line. So to do that, I'm just going to kind of do this. And as you can see, instead of being an antenna, it should be, maybe I need to get a little bit closer, and probably a little bit more even. You'll end up with a circle. And if you do it right, this here is now a balanced transmission line. It turns the open circuit that we had over here into a short circuit, because this is a quarter wavelength long balanced transmission line. So that's why it's hanging over near the short circuit position. I wonder if I can get this a little bit better if I just touch these a little bit closer and try and get them a little bit more parallel. We'll try anyway. But yeah, you basically get the idea. It's your circle you'll see around the outside. This here is what you'll normally see for a quarter wavelength long. So down at 1 megahertz or something, it's an open circuit because there is nothing on the end of this. After a quarter wavelength of transmission line, you should see a short circuit because the signal bounces out, comes back and hits it exactly 180 degrees out, 180 degrees around the circle. We're a short circuit. If I had a half wavelength for this, then this here would be an open circuit again. It would go all the way along. So yeah, a half wavelength would be at like 250 or 280 megahertz, something like that. It'd be back at the open circuit position. So this is a way of figuring out, how long a transmission line is. But there is a special case of what happens here. This short circuit can be a bit of an issue for balanced line. So I'll see if I can set this demo up. Well, actually, yeah, I'll see if I can set a demo up. Alright, so now I've got a few demos with feed line. The first one I'm going to show you is what happens when you have a 50 ohm load. This is my actual calibration load, and I chuck it on the end of the VNA there. As you can probably expect, you'll see it's perfect SWR everywhere, 1-to-1 in the middle. So middle 50 ohms. That's short there, open over here. So it's just a perfect 50 ohm load. Now what I'll do is I'll move the 50 ohm load onto the end of a 50 ohm coax cable. It's not very long, only like 20 centimeters or so, but the point should be made. If I chuck a coax cable that is 50 ohms with a 50 ohm load in the middle, assuming a good connection, again we see a perfect 50 ohms in the middle. Now this here, I thought I bought it was 50 ohm cable. It's actually, where is it? RG59U in Australian there. So that there is 75 ohm cable. So I'm going to put the 75 ohm load on the end. Oh, sorry, a 50 ohm load, I should say. Sorry, on the end of this 75 ohm cable. You'll start to see a difference. It won't just be 50 ohms right in the middle. It's going to do something special. You're going to start seeing some wild stuff happening right here. So, assuming I've got a bad SMA. This NanoVNA has battle scars. But anyway, as you can see, there are points where perfect SWR, down at DC. There's another one here at 65 megahertz, and there's another one here at 133 megahertz. However, while these are good SWRs, if we go up to in between, 100 megahertz there, SWR of 2 to 1. So it flips a 50 ohm load. If you look up here, if I go get rid of the J, hang on, I'll just find where it's actually resonant. There you go. To 100 ohms. I've seen up to like 110. You know, it's roughly double. So this might be not quite a 75 ohm cable. And up here, you'll see it's 50 ohms, pretty much exact. So this is what happens when you have non-50 ohm cable. You'll get some weird impedance transformation stuff going on. But if you use this where it's resonant, you know, exact half wave multiple, doesn't matter. It'll still be a 1-to-1 load. Now the fun begins. I'll chuck on the balance line that I've kind of taped together. It looks horrible, yes, I know, but it's going to show you something similar. All right, and now you can see something similar. This cable is a bit shorter than the other one, so there's not as much rotation on the Smith chart. However, you get a perfect SWR, obviously down at DC. So you know, 1-to-1 there, pretty much. 50 ohms, not much J there going on. Surprisingly, this is kind of not a perfect balance line, but it's not terrible. You know, it is doing the balance line thing. Yeah, it's probably roughly about right. Now, as you can see, yeah, DC, it's basically 1-to-1, and where I've tuned it on 2 meters, it's also basically 1-to-1. However, in the exact worst case, where it's open circuit, you've got 600 ohms. So that would suggest this is something, it's the geometric mean. It's probably like a 200 ohm cable. It might be even 300 ohms, but I think it's probably closer to, you know, 250, 250, 200 ohms with this spacing. The further spacing you have, the more impedance transformation you get. So what I want to do now is I want to take this half wavelength and go convert to a quarter wavelength, and then chuck this 2 meter antenna on the end of that. So I will set that up, and we'll see some stuff. All right, I haven't perfectly nailed the length of the the transmission line. It's rotated up here a little bit rather than over here, but it's probably close enough to see. So the one final test I want to do is I want to chuck the 50 ohm load on the end of a quarter wave line balanced transmission line, and we'll do that. Sorry, we'll plug that in there. If I could, yeah, get that on there with one hand. There we go. Now if we see, so while the load is good down at DC because it's 50 ohms, the balance line has flipped our 50 ohm load up to something like, oh, where is it? We're up to 140, aren't we? 160, hang on, we'll go to the open circuit position. So about 800 ohms. So yeah, or, you know, 150 minus J300 there. Where are we? Go to 2 meters. There you go, 100 minus 200J. So this is nowhere near a good match. So be careful about quarter wave length long transmission lines when you're playing with antennas. I guess the one final check is we'll chuck the real antenna on there and do no transmission line, and then quarter wave, and then half wave, and just as a final sanity check, you'll see what happens. So now we're back to where we started. We have the dipole hooked up, and as you can see, perfect match, because why wouldn't it be? All right, we'll chuck in the quarter wavelength. All right, this is our quarter wavelength line with a dipole antenna, and as you can see, our antenna is gone, just not there at all. Yeah, it's flipped our 50 ohms up to lots, lots of ohms. So she's not working. And here is our half wavelength of our transmission line and an antenna. And as you can see, our antenna's there, and it's a little bit low impedance. So obviously it is messing with it somewhat. Might just be the way this antenna is also laid out and stuff, but oh, there you go. Yeah, 1.5 to 1 SWR there. It's a little bit better here, but yeah, there you go. So there you go. That's a half wavelength long and then an antenna on the end. So it works fine. All right, so that kind of gives you an idea of yeah, balanced transmission lines and how they can misbehave. So that's all I have. 7-3 all, VK4 Delta Lima.